So this is a video to try and take you through exercise 12.7. The first thing I'd be looking at to do is go back and revise section 2.6, particularly the method of how you solve cubic equations and what is the factor theorem again. So anyway, what is a polynomial? Well, a polynomial is something of, well, anything to look down here. The coefficients can be real or complex, but the important thing about a polynomial is the powers. The powers are all non-negative integers, so anything from 5 down to 0. Anything other than that, and it's not a polynomial. So the degree of the polynomial then is basically the highest power that you have. So y equals x squared minus 3x plus 5. It's x to the power of 2, so that's a polynomial of degree 2. So the number of roots in a polynomial equals the degree of the polynomial. Now, and we refer to the conjugate root theorem here again. If the coefficients of a polynomial are real, and if some of the roots are complex, they must occur in conjugate pairs. So now, just to work the example 12.22 on page 299, I'm not going to go through it here. It's just pretty painful stuff. You just got to go to these proofs here, and the general routine is that you would let whatever z equal to x plus yi, and then if it's z1, x1 plus y1i, and just fill in all the stuff there and you try and work it out. If you want more details of that, you can ask me, but I'm not, as I say, I'm not sure how important that is. So I'm not going to worry about it for now. But back to what I consider more important stuff. Work example 12.23. It says here if z is equal to 4 plus 3i, show that the conjugate z bar is which is equal to 4 minus 3i is also a root. So one method is you can sub it in, but the other method is you could take the two roots together, and knowing that the sum of the roots should equal to minus 8 and the product of the roots should equal 25. So for example here, the two roots are 4 plus 3i and 4 minus 3i. And I see I have a little misprint here. So 4 plus 3i plus 4 minus 3i equals 8. And so the coefficient of z should be minus 8, and it is. And the product of the roots is equal to 25. And so therefore the constant term should be 25, and it is. That's just an alternative to that method there. Now the next example, a bit more sophisticated. We've got a cubic here, a cubic polynomial, and it goes through what's the degree, what's the value of n. So the degree of the polynomial is 3, so therefore it has 3 roots. If 1 plus 2i is a root, that's all grand. 1 minus 2i is also a root by the conjugate root theorem. Now to find the last root, the first thing you do is taking the two roots that you know, you form a quadratic from that, z squared minus 2z plus 5. And one method is you can divide it in, or you can go like this. If after making the quadratic z squared minus 2z plus 5, you now know that that quadratic times the linear factor az plus b must equal to your cubic that you were given in the question. And from what you know about multiplying with brackets, so here z, the first term here times the first term here should equal the first term over here. So first times first equals first. So that's z squared times az equals 3z cubed. And from that you can work out that a must be equal to 3. And the same when you multiply with brackets, the last term in the first bracket times the last term in the second bracket must equal the last term over here. So therefore 5 multiplied by b must equal 5, so b must equal 1. So therefore my missing linear factor is 3z plus 1. And then go back up here using 3z plus 1, work out what the root must be, and it equals minus a third. That's just an alternative method to long division if you're not a big fan of it. And now to the exercise itself, I just threw in some questions here. Question 4, the solutions to it, and question 6 is painful. They ask you to work out 2 plus 3i to the power of 4. But I think you should be able to work out from that how you go about doing the question. And I wouldn't bother with questions 12 to 15, but again, if you want more information about them, just ask me. So hopefully that's enough information for you to get you through exercise 12.7.